Hi, today I'm going to talk about our work, Generative 3D part assembly while dynamic graph learning. Part assembly is a very basic and important task in robotic manipulation. And in our paper, we formulate the part assembly task from a vision or graphics perspective. Given parts laid out in the part canonical space, the goal is to compose a full shape. It can be formulated as a post-estimation problem. Our problem setting is parts are provided, no geometry is predicted. 60 part pose of both rotation and translation need to be predicted. We assume no prior knowledge upon the input parts. Such a setting can be applied to the situation where the robot needs to assemble an IQ 12 from its parts, which can be randomly placed on the ground in the beginning without instruction manual. In this paper, we propose to use the dynamic graph learning framework that predicts a 6-step part pose, including a rigid rotation and translation for each input part point cloud, while forming a dynamically varying part graph and iteratively reasoning over the part poses and their relations. In the part graph, nodes are Latin representations for each input part point cloud, and X are the relation weights between nodes. In each iteration, we conduct message passing between nodes according to the X weights connecting them, and then predict the poses for each part based on the node features. These pose estimations are in turn used to predict the relation weights between nodes, which are used in the message passing in the next iteration. In this way, we employ an iterative graph neural network backbone to gradually refine the part pose estimations in a cost-to-find manner. At the core of our method, we propose the dynamic part relation reasoning module and the dynamic part aggregation module that jointly learns to dynamically evolve part node and X features within the part graph. Here are the details of our dynamic graph learning algorithm. We use the PartNet dataset to demonstrate our effectiveness compared with existing methods, both quantitatively and qualitatively. A Bayesian study illustrates the effectiveness of each module of our method. It's interesting to make some analysis of the implicitly learned relation. We can see similar patterns in both even and odd steps. On average, central parts emit more relation weights than peripheral parts, indicating that central parts guide the part assembly process more. We can see from the time-varying part assembly results that the poses for the central parts are firstly determined, and then the peripheral parts gradually adjust their poses to match the central part. Thank you.